So Vesper notation is pretty straightforward. The format for it is always AXE of some sort. Okay? The A represents your central atom. You do not replace the A with the actual formula for the element. It's A. But it's going to represent the central atom. The X represents atoms bonded to the central. And the E represents pairs of electrons not bonded. This, like I said, this is one of the slides. Now, on the rare chance that you do have a molecule that's got an odd number of electrons, remember how we did that with just one dot, it had 7 electrons around it? We would count that 1 electron as a pair for this purpose, okay? Now, for water, here you say, oh, this is really simple. You're gonna say it in your head because you guys are pretty quiet. My other classes might actually yell it out. Oh, this is simple. For this compound, the Vesper notation for water is AX, and we put as a subscript the number. So the A represents the oxygen. The X represents that there are 2 hydrogen atoms bonded to that oxygen. So that's the AX2. E2, because I have 2 pairs of electrons. Not how many electrons, how many pairs. Okay? This will become much more evident as to the why we're doing it this way tomorrow when we start looking at the shapes that molecules take. Okay? Questions? Alexa, pick one of the compounds off of either one, Lewis structure 1 or Lewis structure 2. Just pick one.
HCN.
Okay, so HCN. Is that from the first one?
Yeah.
What number is it?
31.
Okay, so if you want to go look at it. In this compound, our Vesper notation would be this. And that's it. Everybody okay with that? Why no E?
Because there's no electrons bonded to the central atom.
There's no pairs of electrons on the central atom. And that's what all of these, okay, I should say this on central, just to make sure, I mean, it's in your notes, but I want to make sure you guys understand. All this Vesper notation is focused on that central atom. So we're looking at that. So around that carbon, what do we have? We've got 2 atoms bonded to it. There are no lone electrons. Notice I'm not counting lines, I'm just counting how many atoms are attached to it. Okay? So we're not, yeah, we gotta look at the bonds, but this triple bond is only attaching 1 atom. Good choice, by the way, Alexa. Somebody give me another one that's got lone pairs. Brennan, give me a Lewis structure. I don't care which document comes from, 1 or 2.
31 on the second one, PO.
What's that?
PO, 31 on the second one.
Just CO?
PO. Potassium, or not potassium, iron.
Phosphorus.
Yeah.
I'm trying to think if I want to do that one. Okay, pick one that's got more than 2 atoms because we need to have a central. If you've only got 2 atoms, there's no central. We really, so let me back that up. We really wouldn't do a VSEPR notation with that one because there is no central. So anything that's just got 2 atoms, we're going to ignore this. We don't do a VSEPR notation. So go ahead and pick another one.
H3PO4.
Okay. Good one. All right. So when you did that little structure, I told you guys are going to do the oxygens on the central, and then you put the hydrogens from those acids. Brandon, can you tell me what the VSEPR notation is going to be? Why not? Okay. Actually, you know what? This one would have several. Good choice. I get to teach you some stuff, okay? This one had several. Because what's the most obvious central atom? The phosphorus. Okay? So for the phosphorus, the VSEPR notation would be AX. Brandon, I'm going to give you another chance here. What's the X represent?
No.
Well, it could represent anything, but it's going to represent atoms bonded to that central atom, right?
No.
So if I'm taking phosphorus as my central atom right now, how many atoms are directly attached to it?
4.
And that would be it. Okay? Now, we have other central atoms here. Okay? I guess you could say phosphorus is the central atom, but oxygen is also kind of a central atom here. This oxygen, these 3 oxygens, they're at the center of several bonds. Okay? So in some of our more complex molecules, we need to look at what's the VSEPR notation around multiple atoms. So in this case, all of those oxygens are going to be what? Joey? So what would be around that one? AX2 and E2. Now, because they're all the same, I don't need to redo it over and over again. Everybody okay with that? So VSEPR notation is just a matter of counting how many atoms are bonded to the central and how many pairs of electrons are attached to that central. Everybody okay? Now, the close relative of VSEPR notation, I probably shouldn't have done that. close relative to this is called steric number. And again, this is one of these things that we're setting up for material we're going to cover tomorrow. Okay? Steric number is basically the sum of the subscripts that you put in your VSEPR notation. So if this is AX2E2, my steric number is what? 4. So we're looking at these values here to give us that. In this compound, the HCN, oh wait a minute, this was a 2. Brandon, what was that? The H3PO4, what number was that in that document?
25.
Okay. What would be the steric number on this, class? Hold up fingers. Because all we have is the 2, right? We don't have any lone pairs, so look, the steric number literally is just the sum of the subscripts that you would write here. Or you could look at it as it's how many atoms you have attached plus how many lone pairs of electrons you have. So that phosphorus there, what's its steric number? And the oxygen is going to have a steric of what? Everybody good? Okay. Last thing, and I'm going to give you your assignment. I'm going to give you time to work on it. Actually, everybody at home, is stuff working right? I'm not frozen.
Good here.
Any questions from home? What? I don't know if you find any place to sit.
We'll have it.
Okay. Okay. SO2. This is in Lewis Structure 1 document. I can't remember what number it is, but I know it's in the Lewis Structure 1 document. So I'll give you a second to go find that.
It's 33.
Is it 33?
Yeah.
Okay, so in document 1, number 33, and I think in every class, when I think I did this as an example with you guys in class, and I think in every class, somebody asked about, does it matter what oxygen or gets the double bond? Okay, and the answer to that at that time was, it really doesn't matter. And now it's going to be both. Okay, so when we've got to keep in mind, when we're talking about our Lewis structures. They're trying to represent an extraordinarily complex process of bonding. In that, we've got sulfurs, we get the sulfur and the two oxygens. Their electron clouds overlap. When those electron clouds overlap, their energy drops. But the key there is, one of the important things is that when those clouds overlap, it becomes one cloud. The electrons aren't stuck in any one place. So those valence electrons are going to be in that cloud, able to move around fairly freely with some limitations. It's kind of like with, when we talked about atomic theory, that the electrons, they have areas where they're most likely to be. When a chemical bond forms, what we would think of as the S and P sublevels, those orbitals that we learned about in first semester, they kind of go away. They morph into something new that we talk about as molecular orbitals. They're not atomic orbitals anymore, they're molecular orbitals, which are described by areas of probability. People, this is a really, really, really simple, basic way of showing what is attached to each other, but it doesn't show the complexity of everything that's going on. It's a good starting point, okay? So, and I know I mentioned this last time. I said that because I wanted to introduce it at least. If our atoms are going to be attached to that pattern there, okay? And there's a reason why I draw it at an angle like that. Tomorrow you'll learn about that, okay? But if I represent, this is not, the chalk's not cooperating. That's better. If this is my electron cloud, where the bond takes place, or the bonds take place, and the electrons are able to move freely in there, then this double bond really doesn't exist anywhere. I don't have 4 electrons stuck in between these two this sulfur and this oxygen. I don't have 4 electrons stuck between here. I've got 6 electrons being shared in this cloud. And the reason why I drew a little scribbly in there is to represent that in between these atoms, where the bond is occurring, we're going to have a higher density of electrons than out here, because that's where the bond is occurring. But like I said, we don't have 4 on one side and 2 on the other. To represent that symbolically then, it's called resonance. To represent this complex dance that the electrons are doing, we basically draw our Lewis structure out twice. And again, it's not a perfect thing. Because what this is implying, I mean, if somebody's just looking at it, it implies that, oh, well, that means that I've got 4 electrons here and 2 electrons here, and then they just trade places. So if I were to call this oxygen number 1 and this oxygen number 2, and I had the same thing over here, it looks like a double bond switching back and forth. No, that's not what's happening. We don't have a double bond. We don't have a single bond. We've got 6 electrons being shared. But that's the limitation to our Lewis structure. Our Lewis structure is a very, very simple, oversimple way of representing a very complex thing. So why do we use it? Because if I were to go look at a sulfur dioxide and this is why I drew it at angles like this, it would look like that. It would have the oxygens at an angle to the sulfur. We have, with our Lewis structure, some information that is usable that can allow us to make predictions about how it will interact with stuff. Okay? Questions? So here, yeah, Joey?
So if you wanted to do the VSEPR for that, would it be AX3 or AX2?
So we base the VSEPR notation on the structure. And because these structures are equivalent, we're just drawing the double bond on different oxygen, they'd both be AX2E. Because you've got two atoms bonded to the central, and you've got the one pair of electrons. People at home, do you have any questions? I'll take your silence as a no, you don't have any questions. You good? All right, here's your assignment. Both documents, Lewis structure 1 and Lewis structure 2. Oh. I do have one more thing I'm going to, you know what, I'm going to save it for tomorrow. Lewis structure 1, Lewis structure 2. I want you to go through and identify the VSEPR notation, the steric number. Okay, so just write AX, E, blah, 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 and the steric number. Do that for each of them. It's just counting, right? Okay. I also want you to go through and identify those compounds. There's not a lot, okay, that are like sulfur dioxide. And I want you to go through and draw the resonance like this. Okay, so if you've got an atom and I'm going to limit it to this. We would have a resonance structure with the sulfur dioxide because these oxygens are both oxygen. If I were to change this to a sulfur, no, not sulfur, a selenium, which would be the same thing, this would be it. There is no resonance. Kind of a lie, but for what we're going to do at this level of chemistry, we're going to say, no, it's not going to have resonance. We're going to have a double bond here, we're going to have a single bond there. So the atoms that are double, that have different bonds, that you could draw different ways, need to be the same. Okay? Like I said, there's not that many of them, but I want you to draw the resonance structure for them. So when you walk into class, well, when you guys sign into class tomorrow, you'll have that done for both sheets. Okay? For those of you at home, you're going to walk into class with that done, because this is going to be core to what we're going to use tomorrow in class in introducing our structures. Okay. Yeah. All right. Questions? Rest of the time, you can work on this. So those of you who are here, you can, I'll be walking around seeing how you're doing. If you're at home, you can say, hey, Mr. K, can you check these? And I'll have you share your screen with me, and we'll take a look at it and correct anything you may be doing incorrect, or say, hey, you're doing great, keep on going, okay? If you can't stick around if you're at home, I understand. But if you can, while you're working on it, please stick around. And that way, again, if you have any questions, or if somebody here has a question, I may put it up on the board and explain it to everybody, okay? Everybody good? Okay, get to work, and I will start wandering around helping people out. So, because I'm trying to do stuff with Milligan's class,
Oh,
and watching Zoom is choppy as hell. I mean,
Right.
you've seen them.
Yeah.
You know, I'm just recording, straight
Straight
recording,
recording.
and then I'll just download that and I'll edit it down a little
yeah,
bit
yeah.
for those
And then you
students
see
that are
them
in
here
his
too,
class.
like this is the kids. So that
Well,
would-
no, most